Hello and welcome back. This is video 2 from chapter 18, which deals with reactions of benzene. We started last time with our introduction to electrophilic aromatic substitution reactions. We talked about halogenation. In this video, I'll focus on nitration and sulfonation. So here are the learning objectives for this video, and after you watch this video, you should be able to do a little bit more from the problem set, problem number 1, and then problem number 3. Let's go ahead and get started. So just a reminder, in electrophilic aromatic substitution, we have here an electrophile that's reacting with a benzene ring, and the benzene ring here is serving as our nucleophile, right? And we're substituting the electrophile for a hydrogen on the benzene ring. So let's take a look at nitration. So when we nitrate a benzene ring, we end up with a nitro group on the ring. And we do this using 2 concentrated acids. We use nitric acid and sulfuric acid. And so you're both familiar with these inorganic acids. You know that they're strong acids. Nitric acid happens to be a little bit weaker than sulfuric acid. Sulfuric acid is strong enough that it can actually protonate the nitric acid. Nitric acid on its own is not a really great electrophile. So we're going to turn it into a really good electrophile called a nitronium ion. And let me show you how that occurs. So we know this is a stronger acid than this, so this is capable of protonating. This is going to donate a proton. This is going to accept a proton. So let me show you how that happens. So here we have our dot structure, or a Lewis dot structure for nitric acid, and it's going to accept a proton from the sulfuric acid. And when it makes this species here, it can very, very quickly lose water. Okay, so we're going to lose water, and we're going to form this nitronium ion. And this is a great, great, great electrophile. Okay, so this is what's serving as the electrophile in this reaction. So notice here, this nitrogen has a formal +1 charge on it, okay, because it has 1, 2, 3, 4 bonds. It came with 5 valence electrons. It feels like it owns half the bonding, or just the number of sticks, and there are no non-bonding electrons on it. So that has a formal +1 charge. Okay, so let's go ahead and take a look at the mechanism for the reaction. So remember, this is our nitronium ion that's going to serve as the electrophile. And we're going to be substituting a hydrogen on the ring for the nitro group. So in the first step of this mechanism, what do we have taking place? So remember that the benzene ring is serving as the nucleophile. So it's going to attack the electrophile. And then we're going to make a resonance stabilized intermediate that contains an rhenium ion. And again, in Klein, he also refers to this as that sigma complex. So here we've temporarily lost aromaticity, right? And then what will happen in the next step, so we can either use water to do this. I think in Klein he uses water, but since I know I have the conjugate base of sulfuric acid also present, I can also show this as what is going to deprotonate. So I'm going to go ahead and just deprotonate here, rip off this proton, and then this pair of electrons can move here, and we get our nitrobenzene. Nitrobenzene is less reactive than benzene, and it's really important for making aniline. So aniline can be made from nitrobenzene by reacting it with a reducing agent. So let's take a look at that. So this is an important reaction that you also have to know about, even though it's not the electrophilic aromatic substitution. This is just reduction. So we're reducing the nitro group. So I can also call this reduction of the nitro group. Okay. And so aniline is used for lots of different dyes. It's very reactive, and you normally can't just put an amino group on a benzene ring. Normally you put on a nitro group and then you reduce it. Now in Klein, instead of using, so hopefully you're familiar, I tried to pick something that hopefully you have seen before, that you recognize is a reducing agent. So you have molecular hydrogen, and then the catalyst for this is the palladium on charcoal. In Klein, you'll see that he will instead use iron or zinc in hydrochloric acid, and then you end up with an ammonium ion here. And so in the second step, you add a base like sodium hydroxide to obtain the free amine, okay, the neutral amine. So if you're doing the reading, you're going to see it like this. This is how I will show it, just because hopefully it's a little easier for you to recognize that reduction that's taking place. This is a really, really useful reaction, again, for making aniline, because we can't put an amino group directly on a benzene ring. We are going to first do nitration and then reduce it to make aniline. Okay, so make sure you know about this reaction. This will come in handy. All right, then let's talk about sulfonation. Sulfonation uses fuming sulfuric acid. And fuming sulfuric acid is just a mixture of sulfuric acid and sulfur trioxide gas, okay? So Klein will say fuming H2SO4. You're going to tend to see that I tend to write this out because the sulfur trioxide is a good electrophile on its own. It's actually a really great, I'll call it a great electrophile, okay? And we'll take a look at why that's the case. So we can add a sulfonic acid group to a benzene ring, and we get good yields here. This is like 95% yield. You don't need to memorize these yields at all. It's just one of those sort of interesting pieces to know how well the reaction works. And this reaction here, this sulfonation reaction, is really useful. It's one of the initial pieces that we use to then go through a multi-step synthesis to make sulfa drugs like this. This is one of the earliest sulfonylamides. Okay, so this is a really important reaction for making sulfa drugs. Let's talk a little bit about the mechanism for this reaction and why is this is a great nucleophile. Electrophile. Electrophile, great electrophile. This here is our nucleophile in this reaction. Okay, so let's take a look at why sulfur trioxide is such a great electrophile. So in our electron dot structure, and I haven't put in the lone pairs on the oxygens here, but they're there. You see that the sulfur has these p orbitals that are trying to overlap with oxygen's p orbitals, which I'm going to draw much smaller, since remember that sulfur is below oxygen on the periodic table. So in its valence shell, the p orbitals, the 3p that it's using, is much, much bigger than the 2p from the oxygen. And because of this, there's really not good overlap between these p orbitals. So a better picture of what this compound looks like is to imagine here that the sulfur has partial positive character to it. And the oxygen here, I've shown an oxygen with a single bond, has that partial negative character. And so this is still our sulfur trioxide. And again, the sulfur feels this sort of partial positive charge on it due to this not great overlap that the p orbital, the sulfur has with the oxygens around it. So I'm going to go ahead, and our nucleophile, here's the benzene ring. It's going to attack our really nice electrophile, right? And we're going to end up forming an intermediate that has an rhenium ion, surprise, surprise. Okay, so I had a hydrogen here, so there's still a hydrogen here, but now I've added this SO3 group, and now this is going to have a formal minus charge on it. I'm just going to put that there. And so I can draw two other resonance forms for this, and you should do that. So you practice drawing those resonance hybrids. And then in the next step, so I'm going to do this a little simpler than how Klein does it. Klein breaks this piece down into 2 steps. I'm going to break it down into just 1 step. You can use either way on an exam. So what I like to do is just pull off this proton to from this negative charge here. I'm going to pull off the proton. I'm going to restore aromaticity like this. What Klein does is he shows water deprotonating the ring and then protonating the SO3 minus. But we can show it like this, and then we can do it much faster. So when we do that, I end up with my SO3H, which again is referred to as a sulfonic acid group, okay? And so besides being a great way to start the synthesis of sulfa drugs, which are a type of antibiotic, in the laboratory as an organic chemist, we use this sulfonic acid group as a blocking group because it's easy to put on and it's also easy to take off. And that's different than what we see with like bromine or a nitro group. If we put it on, it's difficult to take off. So I'm going to make mine here that you draw. Okay. All right. So this sulfonation reaction is reversible, and that's really, really useful. So we can use, again, Klein writes it out like this fuming sulfuric acid. And you'll see me, I'll say here, or you see me just write SO3 with H2SO4 here, and that's going to mean the same thing. I tend to write it out like this as a reminder to you that this is serving as our electrophile. And then, so this reaction is very much sensitive to the concentration of the reagents, and it's reversible. So I can reverse this process by using dilute sulfuric acid. I can return back to, I can just pop the sulfonic acid group off. So this is really useful. So let's say, for example, I have, and we'll see this later on when we talk about other types of reactions on benzene. So let's take something like this, and I can use dilute sulfuric acid to remove, I'm going to remove the sulfonic acid piece, and I'm going to leave behind these pieces here. So it's much harder to remove a bromo group or a chloro group or a methyl group from a benzene ring than it is to remove a sulfonic acid group. So we can use this to sort of block that position, and we'll see lots of that next week. Okay. All right, so sulfonation is really important because we can use sulfonic acid as a blocking group since this reaction here is reversible. So we can add on the sulfonic acid group, and then we can carry out a whole bunch of reactions. And then when we're done, we can remove that sulfonic acid group. And then it's also really important for the synthesis of sulfa drugs. It's a class of antibiotics. So I think I mentioned sulfanilamide. I'll just go ahead and draw that out again. So this is a competitive inhibitor for para-aminobenzoic acid, okay? And bacteria make folic acid by, they need para-aminobenzoic acid to do that, and they in order to grow, if they can't make it, they're gonna die. So we take advantage of that. Okay, in the next video, I'll focus on Friedel-Crafts. We'll do 2 reactions. We'll do alkylation and then acylation. So that's what's happening next.